So good morning, everybody. Welcome to the last of the 4 webinars that we're presenting today about machinery integrity. And today we're going to talk about keeping your distance using presence sensing techniques. And we're going to focus on a standard and the key principles of that standard that everybody has to follow when selecting these devices. So first of all, just a brief introduction about myself. I'm the product manager for IDEX safety products in EMEA. I've had the responsibility within machinery safety for 25 years, working alongside people from product design and development, and also done a lot of work on risk assessment and allocation of machine safety functions. So I've got a very practical design and engineering experience and worked in a lot of different industries, helping to remediate machines and get them as safe as you possibly can. And I'm part of a team of IDEX safety specialists and automation specialists who help make your production line safer. And today, some of the content of the slides is also contributed by one of our consulting partners, which is Astute Machinery Consultants. And they're an IDEX partner who we consider can assist you in your competence on machine safety. IDEX partners are always here to help deliver know-how, both from a consulting perspective, but also with system integration of the components. So, some questions. Do I need a presence sensing device? Well, as all of the other webinars I've done, there's a very simple question, is have we performed a risk assessment? We need to identify who is exposed to the hazard and what their tasks are, what they're doing on the machine. And then once we know what the individuals are doing and we've made a list of all the people who are in contact with the machine, we have to identify the target. Is it their hands, their fingers? Maybe they're leaning into the machine, so it's upper body. It could be that they have to lean a long way in and there's a risk of the torso, or perhaps stepping inwards would create risk to the lower limbs. And potentially, as for example with robot cells, you have to go whole bodily in to an area which has got a lot of space around it, like a robot. And then once we've looked at that area, we have to say, well, if we want to use a presence sensing device, is there in fact a risk of part ejection? Because of course, once we remove the mechanical guarding that is separating us from that hazard, we have to consider, is there, for example, any risk of swarf being ejected out of the machine as it's cutting? Perhaps material from pressurized processes could be ejected either through a fault or just because it's what happens when you open the tooling. But it needn't necessarily be a mechanical obstruction or a mechanical risk. It could be radiation. It could be the ejection of sparks coming out from a weld cell. So yes, we're looking at a robot and we're protecting against mechanical contact with the robot. But in car plants, for example, you see sparks going 5-6 meters away from the center point of welding. We have to identify there's a mechanical release of parts. So most people think about things being cut or thrown or come as a result of compression. But a robot and a lot of equipment can mechanically let go of it whilst it is in transit. And what is the trajectory? Where will it land? If it's a liquid, it will pass through the air and straight through the front of the presence sensing device. So whilst we look at a lot of the things and we say they might be a nuisance, we have to accept the fact that it will not be stopped by the presence of a light curtain or a mat or a laser scanner. It's very important that the risk assessment details what the machine is going to be used and whether or not there is any hazard as a result. We need to identify the frequency of access, not only for an operational efficiency reason, but also the number of times somebody goes in increases the probability of them being exposed to a failure and a hazard on that machine should a fault occur. But from the manufacturing perspective, we need to identify whether or not we've got large or complex objects moving about the factory. For example, in a car plant, it's very difficult to move a large vehicle on a vehicle carrying platform through a conveying system and allow that to go through but to also detect if a human being is trying to go through at the same time, to keep them out of the spray booze or the welding cells. So we need to identify the size of the objects and how we're going to tailor that plus other devices to detect people going in. And of course, object sizes vary. So whilst you might have a conveyor carrying a box into a machine, and it might be considered okay to put a mechanical guard with a hole in it, if the next thing that goes through is much smaller, now you have a gap between the product that's going through and possibly a human could breach in. So possibly using a presence sensing device might be the right thing, because of course you can adapt it, program it, sculpture the light pattern that's being used to monitor, and identify that object size varying. And of course, there are always logistical issues, because factory floor space is always at a premium. And sometimes just using a presence sensing device can take away mechanical obstructions that consume a lot of space. So the earlier we can detect a human in an area in front of a machine, the better it is. But then we can also say, well, we're more efficient on where we place those devices. Of course, the more people that are working in an area, we need to understand why they are there and whether or not there is a risk of them being inside. And when you're using presence sensing devices, it's quite often the case that there are large hidden areas behind things like robots where other operators can't see. So our means of resetting and our ability to detect other personnel in the area comes into question. And we should always be questioning, is this the right device for the hazards that we've detected on the machine? And of course, at the end of any application, you should always look and see whether or not there is a level of residual risk that you can tolerate. And if you can't tolerate, you go back to the beginning of the process and start again until you've reduced that risk. So once you have an understanding of everything, then you can select your device or potentially revert to another measure. And quite often, you actually revert to a combination of measures between perhaps a light curtain and some guarding and a pressure mat and so forth. So we use presence sensing to effectively prevent harm. And the most obvious thing is we have a gap in front of a machine, and we perhaps put a light curtain across the front of that gap, and that creates an invisible perimeter. Usually it's very obvious because 99% of light curtains are painted yellow and they stand out very clearly as being there for a reason. And it's quite common to combine that light curtain along with other mechanical measures like side guarding and such like. But of course, we can also have protective measures like pressure sensitive mats, and we can use laser scanners which detect and send out a beam into the area. We'll talk about that a little bit more in a moment. But the key to selecting your presence sensing device is stop time testing. The purpose is that we should identify the position of the device in relation to the hazard once we've ascertained the known direction of approach. So from our risk assessment, the man moves from the pile of material to the machine and he walks through in this direction, or he reaches in this direction, or even steps in that direction. And therefore, if we know where he is moving from and to, the next thing is to determine how fast he is going. And that is the approach speed. So it's really important that we measure the real stop time. And not only do we measure the real stop time of the machine, but that we identify the actual machine conditions over its entire life, because it might be that the machine is faster during cleaning. It could be slow at the beginning of the process and speed up as the load starts to stabilize, perhaps in a mixing process or something like that. So operating, cleaning, maintenance, all conditions. And when you perform a stop time test on a machine, you're trying to identify the worst case stopping time. And that is what you use to determine the position of your protective measure, your light guard. So in order to do that, we have to get on to the boring bit, which is the EN ISO 13855, which is safety of machinery. It's a harmonized standard under the Machinery Directive. And rather cheekily, is put there to make sure that it is not your final approach to the machine. And it deals with human approach speeds. But to come back to the very beginning, we do this because the Machinery Directive very clearly states that moving parts of machinery must be constructed in such a way to prevent risks, and the installation of guards or protective devices have to be put in place to make sure that you keep the operator away from that hazard. And of course, you have mechanical guarding, which is covered by EN ISO 13857 and talks about the reach over, reach under, reach round, and reach through, the position of your guards. And 13855 helps you calculate and understand where to locate a presence sensing device so that the machine has come to a stop as a result of that switching off function and then the loss of the residual speed or energy that is present during the shutdown process. And we'll talk about the stop times in a few moments. So we can use light curtains, pressure mats, laser scanners, in fact, any device that detects the proximity of a worker in the workplace, provided that device has a monitorable safety function that complies to one of the harmonized standards of the Machinery Directive. But we shouldn't just consider the light curtains and the mats and the scanners. We also must remember that a fixed guard may also require a stop time test. And you might say, well, why would I do that? It's a guard. Surely when I open the guard, the switch goes click and the machine stops. Well, a single guard, when you open it, does stop, and it does create a gap that you can then place your hand through. So if the machine is going extremely quickly and you open the guard, you still need to put your guard sufficiently far away from the hazard so that it's come to a halt. And if you use things like hinge switches, there is in fact typically a 5-degree hysteresis. And so that you can move that open 2 degrees, 3 degrees, and it won't have switched. And if that's a big door guard, you may be able to get your hand in. And therefore, the triggering point allows quite a depth of your hand to go through before it in fact switches off. And that really brings us on now to the means of detection. So we have some pretty fundamental things. We want to detect people's hands, and therefore typically there is a resolution of 14 millimeters or less of the protective measure. And that means that your fingers, as they pass through, will be detected very early. Likewise, if your hazard is slightly further away or you're worried about the hand going in, then we detect up to 30 millimeters. And then we go for arm and body, and we go through into bigger and bigger resolutions between the light curtain beams. I'll talk about resolution in a moment. Most importantly, that the selection of the protective measure and its output functionality has to be installed in compliance with 13849, the safety related control standard. And typically on most machines, you will find that the architecture would be a dual channel or a category 4 dual channel with very discrete monitoring. The optoelectronic devices like laser scanners and light curtains have a very high degree of internal testing and equipment analysis going on. But you can buy for quite low complexity light curtains for low risk applications, and they're called Type 2. And a Type 2 light curtain is the sort of device that will perform a functional test at the beginning of each time you switch it on and do a reset. Now that's quite similar to when you get into your car and you put your key in the ignition, or if you've got one of these modern cars, just the key in the car. And when you press the start button, a sea of lights comes up. And that sea of lights is all of these systems being tested to ensure that it's okay for you to start the machine, the car, and then proceed. In the really, really posh cars, you get totally dynamic engine monitored systems, and everything is analyzed throughout the complete use of that machine. For example, brake failure and ABS technology and all those kind of things. And that really is like the Type 4, because Type 4 is a continuous process of analysis. And for that reason, we use Type 4 light curtains on the high-risk applications. And Type 2 light curtains are generally allocated to the lower risk applications where should a failure occur after the test, the risk assessments have determined it's only a light bruise, whereas perhaps at type 4 you would be saying that's an amputation or a severe cut. So 14mm light curtains for finger detection, 30mm light curtains for hand detection, 40 for upper, 70 for lower limb. So there we're starting to talk about people stepping forward and detecting the ankles. And then we also have 3 or 4 beam multi-beam detection, where there are extremely large gaps between the beams. And then we come into the area of, well, surely a human being can step through or lean through. And when you are utilizing the large beams, it's for a perimeter, which is considered to be a significant distance away from the hazard. And we do it so that we can make sure we can have easy access for maybe forklift trucks and that type of thing. So what makes up the stop time of a machine? It's quite important that we understand the principles. So the stop time is the time from when the protective measure is actuated, so when I cut the beam or when I step on the mat or stand in front of the scanner, until the process has removed the energy and that risk has gone away. Or if it hasn't gone away, it may have been reduced down to an acceptable slow working speed. So we accept that risk is okay. So it may be going very slow. And it's achieved dynamically by measuring the dwell time between that stop trigger point and the actual removal of energy from the machine. You can actually generate your stop time using software. For example, if people are using complex control systems with motion control and they've got that motor directly coupled to the machine, it's generating the motion. Because of the motion analysis software that exists, we can actually have a very detailed analysis of exactly how long it takes for that shaft of rotation to come to a halt. So it is quite common for people to determine their stop time using their motion analysis. Now, I have to emphasize, you can only do that if the stop time and the motor is actually directly coupled. If it's belt driven, you shouldn't be doing it. If it has some kind of reciprocating motion, you shouldn't do it, because it's unlikely that you're going to be able to detect all of the angular deflection as well as the backward and forward detection. And a very quick check you can do is using a relatively fast video camera. If you know how many frames per second there are, and you can actually witness the triggering, it is not the most accurate way, but you can in fact count the number of frames from the trigger point until you visually see it stop. And if you know that each frame has a certain number of milliseconds per frame, you can then actually determine the stop time. I would not suggest that that is the final result, but it is very useful when you're doing development work and trying to tweak and change all the time during the manufacturing of your machine. So let's have a look and see what it actually says in the standard about stop time. Well, there's 2 numbers you need to remember, 3 I suppose. Letter is T is the total stop time, and T1 plus T2. And T1 is the actuation of the device, the putting of the hand through the light curtain, and that light curtain's response to actually shut down its output. And once it's shut down its outputs, it's going to turn off things like a safety relay. The safety relay is going to feed to the PLC, which is going to switch off the primary switching elements, which is then going to turn off the final drive. And then if there is any residual energy, finally we get to the termination of the hazardous machine safety function, which is C. So you have T1, chopping the device, stepping on the device being detected. Then you have the sum of the items that are in the control cascade to shut it down. And then you've obviously got the physical movement and things that step away. So you need to make a design analysis. The design phase, you need to make an analysis and understand approximately where you're going to be. But it's really important that the final installed piece of equipment is tested. And also, periodically it is tested, because as bearings wear, as machines bed in, then the rundown times continue. Maintenance may fit a new variable speed drive, for example, and as a result, the frequency may have been 55 hertz or 60 hertz instead of 50 hertz. Well, that means that the machine is running faster. If it's running faster, it may mean that it actually takes longer to run down because of the 20% increase in speed that would project. So reasonably regularly, maybe once a year, once every couple of years, do a test to make sure the machine is actually still working in the way you expected it to be. And as I've said on every single presentation, you do a risk assessment whenever you make a change on a machine's function. If you change its fit or form, you need to also go through and make sure that your light curtain is in the place that it should be, that was intended by the manufacturer when they designed it. So the stop time is the total of all of the responses in that control chain to that final cessation of energy. So it's possible that we might want to combine measures. For example, in the bottom right, you see there's a light curtain, and that light curtain is combined with mechanical guarding. Now, it makes sense because I think we all understand light curtains are pretty expensive devices, and a robot can aggressively make mistakes, especially during programming, and it makes sense that actually if you need or you have a risk of part ejection or side ejection, you put the mechanical guarding in. It is a cost-effective way of doing it. However, if space is an issue or you need access from multiple directions, it's quite conceivable that you could put in light curtains either in the vertical like shown here, or you could put them in the horizontal as well. And one idea is to actually have the light curtains right back out of the way, and then you simply put mirrors in the two leading corners. If you cascade, you can get great flexibility in the workplace. You can get multiple operator access going in from multiple directions, which is useful in a two-operator environment where you've got left and right feeding. It's very flexible, but also has to be taken into account in the risk assessment because anybody can walk into that zone. If we project the light around the machine, we can do it. It's quite easy to do. But we have to remember that as we project it around, each mirror you go through can lose as much as 17% of the range. Now that is actually really quite important because if you've got a 10-meter light curtain, you go through a mirror, that mirror then takes away 17% of your sensing range, and the next mirror takes away another 17%. So if you install light curtains, you need to do it in such a way, and I talked about it before, about the automotive industry of moving products through, but detecting the product, but not actually ensuring that the person can pass through next to the product that's going through. And that way we introduce muting. Muting is a deliberate suspension of a protective measure. And it has to be temporary. And it has to be designed to avoid accidental or deliberately of an operator entering. So when a light curtain is triggered, you'll notice there are muting sensors on the illustration. They detect that there is a vehicle approaching, and it forms a controlled cascade of temporary shutdown of the light curtain and then a controlled reinstalling of the light curtain. And it's important that the spaces to the left and to the right of the conveyor and the product that is there, it's really important that people cannot walk through those gaps. They can't use other objects to try and trick the sensors. Because if you pick up a cardboard box and walk through the beams, you will look remarkably like a car or a cardboard box, and you can then trip the device in a safe way and get in. So the positioning of the beams is absolutely critical, and they have to be monitored, and they have a suspended, they use a monitoring technique and a monitoring relay that is preconditioned and set up to try and stop people from triggering and tripping and cheating on the application. And you often need mechanical guarding and additional measures to prevent people from getting in. So giving them large amounts of space either side is a bad idea. But there's always the case where you fit your protective measure and you think you've done your calculations right, and you need to pass the conveyor through. And we've got some nice flat products there on the conveyor, and we want to pass the conveyor through, and we need to use a thing called fixed blanking. But when we put the fixed blanking in, we actually have to teach the light curtain to ignore the structure that is put inside it, because obviously the light curtain currently in that application would trip it. So we install the guard, we install the light curtain, we install the conveyor, and then we have a situation where it won't work. We go in and we program out the beams. So once we've taught it, it ignores that intrusion. But that also means that to either side of it, there is now a gap. And if, for example, that was a 14mm light curtain and we've cut out 2 of the beams, we've now got a gap of 14 plus 28 plus 14. That is enough for me to get my arm through. So if you look at the left-hand side of the illustration here, you'll see a square, and that is to represent a piece of mechanical guarding that has been put in there, because currently the resolution is not 14mm, it's arm detection, it's up at 40mm, and therefore we'd have to move that guard substantially further back from the hazard. So it kind of makes sense that if you chop away beams, you have to install mechanical guards to make up for that loss of detection capability. So it usually requires that additional. I've got to say, in my sort of 8 years of consulting prior to this role, nearly every time I saw blanking, the customer had forgotten to install the mechanical guard. And when they had moved the guard away from the machine, they had failed to put side guards in to prevent people from reaching around. But a lot of applications aren't as cut and shut as the fixed blanking. And if you go into the metal stamping and pressing environment, you will see a reel of material being unfed, or in the paper industry, a reel of material being unfed, going into a machine, and it will flex and it will go through light curtains, and periodically, yes, it will trip the beam. So for that, we have a technique called floating blanking. What happens is that as it cuts a beam, the beam above or below it can then dynamically be switched off. So if we cut one beam, the one above it or below allows a non-tripped condition. And it allows it to flex, because as the material goes slack, it will drop and it come back up and go back down again. So this gives us a very dynamic condition. But again, like with the other one, because I'm allowing one beam above and below to be switched off, I've also now increased the resolution. So it's a very flexible thing, but you are guaranteed now that you need to move the light curtain further away, because again, our 14mm light curtain can no longer detect our hand, because if we put our hand next to the material, or in fact we just put our hand through at the same point, we can in fact create a trip condition, a non-trip condition, because we can get through this large gap. It will only work at the beam that is cut, the one below or the one above. So you can't just reach in at the top and get it to mute. It will only be floating blank in that place. So it ignores the intrusion and allows the material to flow and flex going through. If anybody wants to be one two behind them, they can. Hello.
Sorry, Oh, we've lost Tim for a moment. Do apologise. Tim, are you back with us?
I can hear you. Can you confirm you can hear me?
We can hear you now. If you can go back a couple of slides, sorry.
How far would you like me to go back, Andy?
Just one slide. Yep.
This one?
Yep, that's it. Thank you. Thanks.
Okay. Oh, right. So did people not hear about the free prize giveaway? Okay.
No.
Oh, well, I've won it then. Okay. So I'll go back to floating blank. I'll just leave the text as it is. Floating blank allows people to have an object pass through a light curtain, and as it passes through, it will cut the beam and, of course, will cause a nuisance trip. But with floating blanking, we're going to cut that beam and the one above and below it. And that effectively gives us the opportunity to give flex in whatever it is we're passing through. So you see it in the paper industry, and you see it in the metal industry for stamping and pressing. Also, in the sheet metal work, you can place a piece of metal through and the jaws will close down. And as the bend is being put in a press brake, it requires the operator to lift the piece of metal upwards. And of course, as he lifts it, it will trip the beams. But by doing this, we trip one beam or two beams. We still sustain safety, but we have a slightly wider resolution. And so we bring the curtain a little bit further away from the hazard. And I'll repeat what I said before. There is a fault on this drawing. There is a little deliberate error in there. And I'll just allow you one more moment to have a look at it. And if the first email that I get that is telling me exactly what the error is on that drawing, I will post off to you one of our brand new HR6S relays. And then you've got the fastest safety function that you could achieve using a great safety relay. So laser scanners. These allow a lot more flexibility because they can look around corners. As you see here, this one could look at 270 degrees of angle. We can teach it to ignore parts of the machine and be very flexible in the environment around it. It's used in areas where you have very complex pieces of equipment moving in and out. And also it's ideal if the structure and size of the machine changes, determined by maybe a vehicle being there, or the size and the width of it changes. So it's quite dynamic because you can program it with different patterns and it automatically adopts the new pattern that you've programmed in. Plus the fact that they can monitor encoders gives you the chance to identify speed, direction, rotation, and even use it on mobile applications. Most important thing in relation to EN ISO 13855 is the detection and the safety detection range. So our scanner has a 5-meter detection range, but what's neat is you also get a dual warning zone, and you can get up to 20 meters of warning in front. And that warning can be used to give different speed conditions and such like, and we'll cover that in the next slide. Now, the laser scanner, people tend to visualize it as being something that's multi-directional and multi-angular. It's not. It's a single slice over 270 degrees. It's an ideal thing for laying on the floor, and as people walk up to a machine, it's going to detect them at ankle height and change the control environment of the machine to make it safer. But you can also use it as a dual control. So if you've got two robots and you're trying to calculate your approach speed for that, it's quite nice to be able to say robot 1 continues working at full speed, robot 2 is being actually taken to a stop condition. And if you've got the dual warning zones, you may have done a stop time test, you've done your risk assessment, and with your dual warning, you can say, okay, warning zone 1 brings the machine down to a slow, safe working speed. On a robot, that might be 250 millimeters per second. And operators can then be close enough to make a visual inspection without getting too close. If you get a little bit closer, then the alarm bells go off. And then if you get to the final point, then you get a trip condition. So they help maximize on floor space and efficiency. And overall, they can be used in a very dynamic way compared to the fixed allocation that you might have in a light curtain. So all of this is all targeted at keeping them out. That's what we're trying to do. So operators may either accidentally or intentionally try and bypass the safety measure. So the goal is to detect the ingress of a person in front of a machine, and we're trying to limit the reach over, the under, the round, or just passing through so fast that in fact their hand reaches the hazard. And because of that, there are calculations that we need to do. I'm sorry, we're getting to the boring bit now, but we do have to make those calculations. And if you look at that photograph at the bottom of the page there, you can see that that light curtain is actually suspended quite a distance above the conveyor. That means that operator can in actual fact reach underneath and touch the area immediately behind. So how far he passes through and how far he can reach through before he's being detected is a critical part of selecting a presence sensing device. So just going to touch on the key principles of selecting the device and the calculations now. These aren't all of the calculations. This is a 55-page standard. We would be here a lot longer. But I want to touch on the principles and the numbers that you need to take into consideration. So if you've got a detection zone, a light curtain where it is less than 40 millimeters, you need to use the calculation S, the final safety distance, equals KT plus C. Now, I know you're all going to remember that, so I'll just run through exactly what that breaks down into. Right, K is a constant. It's the human approach speed. If you don't really get an idea for what the human approach speed is, reach out and take your Apple iPhone and just nudge it to the edge of the table. And then with your index finger, flick your iPhone as if it's going to smash on the floor. And I can assure you that you will reach out at 2000 millimeters per second. It is the human reach and grab speed. The next thing we need to do is identify the time. Now, I've spent quite a lot of time already talking about that, and that's why, because this calculation requires us to identify the total stopping time from when we cut that beam until hazardous energy has gone away. I won't go any more about that. But then we have C. We have to add this factor in. What we're doing is we are using it to determine how far the human can get through the protective measure. So the letter D, I'll just highlight that with the cursor here, that is the object resolution of the light curtain or device that you've used. And in that instance, if we put a 14 millimeter curtain in there, that would be 14 minus 14 multiplied by 8, comes up with a number of 0. So it can never be less than 0. And the reason it says never less than 0 is because a couple of countries in the world actually have 12 millimeter resolution in their standards. That means you would end up with minus figure, which is not acceptable. So the D is the sensing capability, is the resolution in millimeters. And we use 2000 millimeters if the hazard is going to be less than 500 millimeters away from the protected device. If the hazard is more than 500 millimeters, the human approach speed is reduced because now we've got movement of the upper torso as well as the kind of snatch reflex of the hand. And then the human is got to make a little bit more movement. So we reduce the human approach speed down to 1600 millimeters and we substitute it. So that is for vertical axis, the most common way that light curtains and protective devices are installed. But when you go up in beam resolution and beam separation, you now need to accept the fact that a lot of you can get through that light curtain before you're detected. And for that reason, we use the 1600 millimeters in the same calculation, but C becomes a constant. And it's constant because we know that the human arm, which is considered by the standard 13857 to be 850 millimeters, that the typical human arm is 850 mil, and you can reach a long way through prior to you actually getting detected. So C then comes in at 850 millimeters. So you need to address the type of light curtain to make sure you've selected the correct calculations. So S equals KT plus C is the basic one, but then C has different values depending on the technique that you're using. Don't often see the parallel axis, but I do see it in automotive industry where we've got the equipment that lifts up and flips over, like inverting service tables on robotic cells. And that's where you mount that light curtain in a horizontal position. Now we have the issue, of course, that the height of the curtain and the trip point is likely to be your waist. So we need to consider how far the human can reach over. And in that instance, we've got 1600 millimeters again because of the slower, the bigger safety distance. But now we have 1200 millimeters coming into the equation because of the articulation of the body and the additional reach of the human arm. And it can never be less than 850 millimeters. Plus, in addition to that, we need to take into account the height of the curtain because clearly, if you can crawl underneath it and reach up, there is a risk that you have increased the hazard and you've allowed someone to get much, much closer. So you need to take that into account as well. So finally, the next thing to discuss is whether or not angled can be utilized. Now, angled is quite useful because you can gain a good protective area. You can get it a lot closer to the machine. It allows you to protect downwards in front, so that lowest beam has to be taken into account, and the first trip beam as well. And it's great when operators are carrying a piece of work in their hand and they can hold it down low, approach the machine without creating a trip condition. They've got the workpiece in their hand and then they can lift it up and enter it in. And as the body and the arms come into the zone, they're going to be picked up by the angle of the curtain. But there are conditions for setting it. And if you set the angle wrong, you then have to revert back to the calculations that I showed you initially. So if the light curtains are positioned at angles greater than 5 degrees or less than 85 degrees, then that's considered to be an angled axis. But if it's less than 30 degrees, then you have to default back to the vertical. And likewise, if it's greater than 30 degrees, then you have to default to the horizontal. Most importantly, the position is that first beam. That first beam where the end of the protective limit is, that has to be absolutely in the right place. Otherwise, the human, as they walk in, won't be detected early enough, taking into account the fact he's got his arms out in front of him and he's holding something. Every time, make sure that you determine the access. And I've talked about mechanical guarding. Is there a way of going around it? Because there's no point in putting a light curtain in if you can just reach around the sides. I'd say that was about number 2 on my consulting failure list. People simply able to place their hands around the protective measure. So coming towards the end now, and we do need to remember a few things about setting and the sort of things we need to do to utilize the machine, the light curtain. When you've installed it, obviously do your stop time test, but we need to make sure that if we've got multiple light curtains, that they're not looking at one another. Because if the left-hand transmitter is being received by the right-hand receiver of another machine, it will fail. I installed some on a Friday afternoon, and by Monday morning, it had completely failed, and we couldn't work out why. And when I went in on Friday, there were 3 machines in a row. And when I drove all the way back to the factory, the middle machine, machine number 2, had been decommissioned and removed. And my light curtain was now cross-talking with machine number 3. So it's important to put a mechanical obstruction in. I, in fact, had put a mechanical obstruction. It was another machine, but nobody told me they were moving it at the weekend. So make sure that you don't get crosstalk. And a great deal of light curtains now have digital coding, so we can code the beams. That allows us to filter out that crosstalk. But that doesn't mean that you're not being picked up by another manufacturer's light curtain. So once you've made the installation, it's really important that you use the black rod that comes with the light curtain. It's called a test rod. And that test rod is used to trip the beams and create a rotation. And you go around and make sure that in a figure of 8 pattern on its side, that you check it from top to bottom, left to right and down, top to bottom, left to right and down. If you achieve that test, you can then be assured that every part of that protective area will save your hand, your arm, or ultimately your life. So as a summary, make sure you assess the risk, do your stop times, remember that you're measuring not only the depth, but the height and the width, the distance apart. Ensure you've got your safety distance calculations correctly done. Install the device, make sure that the lenses are clear, make sure that they're protected against impact. Do your tests annually or sooner. There are no specific recommendations, but you should do stop time tests at a period of time where if you've done a risk assessment, and if the machine is likely to be in an aggressive environment at a greater frequency. Now, if you look after your light curtains and you install them properly, they will be in there for a great deal of time. So this is the last of the webinars, and I just want to wrap up with this last slide just to go back to remember, this is about the safety life cycle. It starts with the machinery directive. You do your risk assessment, ISO 12100. You look at how fast the human is approaching and the guarding. I should have put 13857 there as well. The guarding is important. Once you break the guarding, you create an aperture. You need to use interlocks. Those interlocks might need to be timed or delayed. You then look at the control. You analyze that control. You look at the safety-related control function and check its integrity. And then you can put a big tick in your box and say, I've looked after the safety life cycle. So thank you very much for your time. As I said at the beginning of the presentation, some of these slides were presented in conjunction with Astute Safety Consulting, Machine Consulting, sorry. Leslie's contact details are in the side there. We have many other companies within the European Union who can assist with your risk assessment. And if you've got any questions, I think Andrew is going to step in now because he's been looking at the questions. And thank you for your time so far. Do we have any questions, Andrew?
Hi there, Tim. That was brilliant. You learn a lot with your sessions, which I really do appreciate. The vast experience you've got. I'm having a look through. I've got a couple of questions. I'm just waiting for some questions to come through.
Sure,
so if you don't mind,
that's right.
the first question I've got, you might have said it earlier on, but what's the difference between a Type 2 and a Type 4 light curtain?
But I'll come back to that analogy I said, but the difference is integrity. The Type 2 light curtain does a really good start check, but it's not dynamic and it doesn't test between cycles. Whereas a Type 4 light curtain is going to be constantly on check, 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 so that if a fault occurs, it will find it. Whereas with the Type 2, it will only find it the next time you put a test on the safety life cycle. So you wouldn't be putting that in front of a press that's going to take your pinkies off. But you might do it on, for example, a packaging machine where the severity of injury is a light bruise.
Right. Okay. Great. I've got a question that came in. Which countries have 12mm resolution? Are you able to answer that?
Yeah, I think it's Sweden or it was Sweden, and I think it's the United States have it in one of their standards, though they may now have conformed over to 14mm, but it has been in the past 12mm, and if your calculation comes out at less than 0, you just default to 0.
Right. Okay.
Yeah. Good question, that.
Okay. Which UK will UK continue with the ISO standards? You know.
Fantastic question. this is really, really good. So we could do a whole webinar on UK CA.
Right.
Okay, right. And I'm going to answer it, all of it. The European Union has the machinery directive. The United Kingdom has always had the supply of machinery regulations since 2011, strangely. Now, within the European Union, you used harmonized standards, EN ISO 13855 and so forth. We, within the United Kingdom, will continue to use EN ISO standards because they are the best practice. And they are held in law within the UK under the supply of machinery regulations. And if you were to read the supply of machinery regulations, the latest adaptation, and read the machinery directive, you would think you were reading the same documentation. The fundamental principles are aligned absolutely through the same way. So if you build a machine outside of the UK and want to ship it in, if you built it to CE marking and then apply the relevant UK CA marking, you will have complied automatically. I'm not saying there's not a lot of paperwork and documentation to do, but from a technical perspective, we haven't got any different standards now. I hope that answers it. That should have been a 44-minute webinar, that one.
that was perfect. Even I understood that, so that was great. Sorry, just going back to the type 2 and type 4. Just sort of on the back of that. Does that depend on the category of risk?
It's typical that if somebody has done a safety-related control risk assessment 13849, if they have found a risk requirement of a low performance level and a low category, that it might only be category 2, typically they then select a type 2 light curtain as well. And the architecture of a type 2 light curtain lends itself to the proof testing and the functional testing that lower level of architecture requests. So invariably, if it's type 3, type 4, it's going to be category 3, category 4. If it's category 2 architecture, then it'll be type 2 light curtain. If anybody wants to actually repeat that back to me, they'll be welcome. It's very hard. It's a shame that they use categories and types. There was one point that I wanted to add, a question from Tim Hall to Tim Hall. When you make your calculations and you've identified your stopping distance, if your stopping distance is calculated to be less than 100 millimeters, you still have to adopt 100 millimeters. I did a machine once where we got a fantastic stop time using some pretty complex motion control. And we got it down to 65 millimeters, but we couldn't use it. It was a waste of energy, all the programming, because the minimum requirement is 100 mil. Now, unfortunately, machine builders, and especially modern machine builders, aesthetics means a lot. So a light curtain is fitted on the outside of the frame because it looks good rather than that's where it should be. And I have repeatedly found light curtains inside 100 millimeters from a moving part of the machine, practically every day of the week.
Okay, brilliant. Sorry, just on that topic, sorry, can you just explain a little bit more about stop time test equipment?
Yes.
While you were saying that.
Yeah, well, there are manufacturers of equipment. I don't work for this company, but I've used one which was made by a company called ASM. And ASM produce the devices that I've used, and they have rotary analysis tools. They have linear analysis tools, because if you've got something going backwards and forwards and it's changing direction, we kind of have to accept that it has to accelerate, hit top speed, come to its end stop, decelerate at that point, and then come back. Now, that could be linear, so it's going backwards and forwards. But if it's on a rotating wheel with like this kind of motion, Then what we've got is reciprocation. So it's towards the camera, that looks like I'm punching you. With that reciprocation, what you've got is an angular movement, which is effectively something's moving up and down, plus backwards and forwards of the pistoning action. So if you use a device that's got dynamic monitoring, they have integrated little servos in them. And when you do that test, that servo will calculate the maximum velocity that the moving part achieves throughout that reciprocation. So you have to use either one of those tools or motion analysis if you've got the motion control. It's really important that you identify the fastest moving part to the protected and its distance. And I do emphasize, make sure that you consider it on a machine that is run in. And periodically you do get spurious results. So the minimum I would do is 10 tests on a machine. And occasionally you will get one that seems to be really rapid. And if I get a really rapid one, then 10 becomes 20, because I need to find repeatability. I need to find the average. And I did mention, and it was a real condition, if somebody changes a component like a drive or a gearbox or a frequency inverter, and they have not reinstalled it the way it was in there before, there is a risk that the stop time will change because of an engineering change, which is why you need to do a risk assessment and pick up on those reasons, the things that are going to change the dynamics on the machine. I've seen it, and it really does happen.
Okay, brilliant. Could you go back? I think it was slide 14. You asked a question with I think you offered a giveaway for a correct answer.
Well, hold on a minute. You were supposed to. You got given. Okay, right. There is a deliberate.
I think it was slide 14
on that slide, and the first person who I will say who it is afterwards, who emails me after this.
Yeah.
If you're telling me what your application is and you're looking for a safety relay, I'll send you one. There is something wrong on that drawing. In fact, there's two things wrong with it. If you get both of them, you're still getting one relay, but there is two things wrong with it. In fact, if I'm really honest with you, there's three things wrong with it, because it's only a graphic. But when you are doing machinery consulting like that, you spend your life trying to find fault in other people's work. It's not necessarily the most rewarding, but it is essential that we sit back and review what we've done when we've installed safety kit. Validation, validation, validation.
Right.
Okay.
So, very, very, very last question from me.
Sure.
Slightly different. Is there a minimum height that the top and the bottom beams should be where you walk in?
Okay. So what we're concerned about is we want to make sure that people can't climb over guards. So typically you'll have guards 1800s or 2 meters high. There'll be a gap underneath it. You can buy 1800 high light curtains. Everybody produces them. And of course that top beam has to be there to prevent people reaching over. So let's first of all talk about the top beam. Within the standard 13857, it talks about the distance of the hazard behind the protective measure, mechanical or light beam. And your arm can reach over, and you can articulate at your shoulder, your hand, your wrist, and also, sorry, my arm was out of shot, but your shoulder, your hand, your wrist, so like this. So if that's your top beam, then you're concerned if somebody can do that, and that's, though your arm is 850 millimeters, there are specific calculations. And as the top beam gets higher, then the distance to reach over becomes more and more difficult. So there are tables that you can use that allow you to say, this is the height of my beam, this is the distance away, and it's really easy. You just go from left to right across, and you can make that calculation where your top beam is. The big question is what is the height of the bottom beam? And that really depends on the application that you're using it. Typically, people put it at 300 millimeters, but most people find that there is a risk that people can get underneath. And for that reason, people very often set it at 200 millimeters. I'm going to be quite cheeky now with something I've done, and I've said to somebody before, if you want to know how determined someone is to get underneath a protected measure, leave a €20 note on the floor inside and just stand back 30 meters and watch what happens. And you will find people limboing underneath the guards, reaching in. So it depends. If it's in a machine application, then 300 millimeters. But if it's in an application where it's a non-machine, but it also involves children, then that may go down to 200 millimeters, or may in fact go down to as low as 50 millimeters, depending on the application. The ideal thing at point of operation, like you're looking at in the slide here, is that there is no way you can get underneath it, and the bottom beam is right at the bottom of the aperture. That's the absolute best way to do it.
Okay, brilliant. It all depends on that determination. It seems.
Yeah, €20 normally finds that sorts the wheat out from the chaff, as they say.
Fine.
But
okay.
yes, you will often find the top beam of a large light curtain aligned with the top of the fence.
Right, fine. So last question from me, and I think that unless there's any more questions that come in, so if you didn't have stop time measuring equipment, so if you didn't have that, is it good enough to rely on the calculations of a safe distance figure, or using a high frame per second video?
When you use stop time test equipment, it actually has a dynamic comparator built into its electronics. So, for example, you not quite sure where to position your light curtain, so you use an emergency stop, and that is the trigger. So the moment you press that emergency stop button, you wire it back into the machine, and you substitute the light curtain, and you can create a stop condition. And at that point, you know that is what creates stop. And then there's a comparator timer going on. So the ideal is to actually use something that physically controls the machine. If you do it with a video, you are seeing the hand moving, but what you can't identify is the time from when the hand moves to the contact of the e-stop and then the trip point. So it's visual, and there are some anomalies. So you know your light curtain, for example, might be 8 to 10, 14 milliseconds in switching time. If you do it using video, you have to put some margin in there. It's as long as you've got a massive margin, you're okay. But if you're doing it like point of operation, like in that illustration that happens to be on the screen, that's so close to the hazardous motion on the machine, you should do it properly. Video can be used, but you need to be careful. The motion side of it is fine as long as you've got direct coupling to whatever it is that's spinning on. The nice thing about it, of course, is if you've got freewheeling of a motor at the end, the encoders in the motor are still feeding back to the software and giving you a dynamic analysis. So I actually quite like using the motion analysis, and it's really good on complex machine control systems, especially when you can't see the bits moving because they're invisible through speed.
Okay, brilliant. Thank you. Thanks, Tim, for that and answering all the questions. Thank you, everyone, for your time today. Once again, Tim has offered a gift, a prize. So take him up on that. Send him an email with the answers to his question, and we look forward to seeing you soon. Okay, Tim.
Thank you very much.
Parting words. All right. Thanks, everyone.
Thank you. Bye now.
Bye-bye. Bye.